This lesson is AP Calc 6.2. It's on U substitution, and you might want to pause so that you can read this little story. And then there are 3 warm-up questions, practice AP problems. So again, you can pause and then copy these down and do them on your own, since we'll be doing them in class. Oh. I'll go back. I went too fast. So pause. Then you can pause and write that one down and do that one. And then that brings us to 6.2. So there's an integration technique that's often can be used, and it's called substitution, or I call it U substitution. And so U substitution can be used it's basically the chain rule in reverse. It can be used when you have an inner function g of x, so you have f of g of x, and then there's also g prime of x is part of your integrand. So the integrand is this whole thing that you're taking the integral of. So, and I would say at this point you could just copy this down, and then as we do the examples, it'll hopefully make sense. And we'll be making the inner function u, and then we will be differentiating the inner function, and we'll be getting it into this form, f of u du. And then this is a form we can integrate, and then after we integrate, we'll replace the u with the g of x. So that's the basic idea. Oh, before we do that though, there are 3 more integral formulas that we need to know, and I believe these might just be our last things that we have to memorize as far as differential and integral rules go. So please copy these down, and we need to memorize them. And one of the biggest reasons is just on the AP exam to save time. If you do encounter one of these, if you have these rules memorized, especially on a multiple choice question, you can just give the answer and then move on to the next question. And so that these make more sense, let's talk about them a little bit. So recall that if you want to take the derivative of arc sine of x, you have to think back. Hopefully, we memorized these. Hopefully you used to remember them. That was, let's see, that had a square root in it. It had 1 over, it was the square root of 1 minus x squared. And then dx. I'll just put dx there. Let's go ahead and do the others too. Let's do the arctan. The derivative of arctan. That was the easier one. That was, and I should probably do these with u's. Let me put u's in because that's how we memorized them. That was just the 1 over 1 plus u squared times du, so I'll just write du on top. Then the last one was arc secant. Arc secant of u. I'm really hung up on x's. That's the one that had the u out front, the absolute value u out front, and then it had the square root, and then the u squared minus 1, because these u's are next to each other, and then du. You could pretend that these are u's as well. So those are the ones we already know, and then if you were to work backwards and integrate both sides, let's do that with this really pretty blue color. Integrate with respect to x and integrate, well, with respect to x. Anyway, you would end up getting the integral and this differential would cancel out, and you'd have arc sine equals 1 over 1, the square root of 1 plus x squared. Well, you can see that is roughly right here. The difference is that instead of using just u here for the argument, we're going to think of it as u over a, because sometimes you'll have a constant there, and then if you already have this formula, you'll know how to handle the constant. So instead of 1 minus u squared, we're going to have ends up being the constant squared minus u squared, in case you're wondering where those come from. There is a proof we could do, but it requires u substitution. It's kind of tedious, so I'm just going to hope that you can just accept these rules. At least you can kind of get the basic idea of where they're coming from. We're just considering, instead of 1, we're considering it to be a constant. Now this is going to be our first example for using u substitution. So hopefully you see an outer function and an inner function. The outer function is the square root, the inner function is 4x minus 1. When you're using u substitution, sometimes it's a guess and check game, but so you can try things for u, and a good place to start is make u be the inner function. So 4x minus 1 is the inner function. Then right away, take the derivative of u, and I want to see you guys writing that down. So du equals 4 dx. Please put the dx on there as well. Then you come back up to your integral, and the goal is to replace everything, write everything in terms of u. So the goal is to write the integrand in terms of u. I always say usually to write everything in terms of u. So I'll bring down my integral symbol. I've got the square root, the 4x minus 1, this is u. So I'm going to replace that with u. And then I've got this dx here that I have to replace also, because everything needs to be in terms of u. No more x's. Well, down here I have du equals 4 dx. This is a formula that I can use to rewrite dx. So what I'm going to do is solve this for dx by dividing both sides by 4. So then I have a thing that says dx, an equation that says dx equals du over 4. So this dx right here I'm replacing with what it's equivalent to, du over 4, and I'm going to put it as 1/4 out front. It's nice to have the constants out front. So what I've done is I've rewritten this entire thing in terms of u's, no more x's. And then we can integrate this. So this is best done by writing it as u to the 1/2 du, and then integrate using the power rule. So the 1/4 carries along, and then I'm going to be adding 1 to the power, so that's going to be 3/2, and then dividing by the new power. Dividing by 3/2 is the same as multiplying by 2/3. And then plus c, if you read the joke at the beginning, got to remember that, plus c. The 2's are, the 2's going to cancel, so that's going to be 1/6. And then the u, I'm going to replace it, substitute back in the 4x minus 1. The 3/2 plus c. So this is our answer. Here's another one. If you want, you could pause and then try it on your own if you think you're ready. Okay, so looking at this, you want to look for the inner function to try that as your u. So I see right here I've got x squared plus 1. That's a good candidate for u. Now immediately take the derivative. So you want to find du, and that's going to be 2x dx. Get in the habit of including the dx. Then we look up at our integrand, and we're going to rewrite all of this in terms of u. So we start with our integral symbol. We've got x squared plus 1. That's u. It's being squared. And then we have this x dx that we have to replace. So then I'm going to look down here at my du. Du is 2x dx. I can do this a couple ways. I can notice that I've got x dx here. I could solve this just for x dx by dividing both sides by 2. So that would be, because that would cancel, and then x dx would be the same as du over 2. That's one way to look at it. Sorry. Whew. The other way is, let me come back to the du equals 2x dx. What you can do is solve this for just dx. So you get dx equals du over 2x. So this is the other way. I should probably change up colors. So I'm going to start back at the beginning. I've got the integral. My u is squared. Then this x here needs to be brought along. And then I'm going to replace the dx with this du over 2x. And notice if you end up doing it that way, the x's will cancel, and you'll end up getting the same thing that I got doing it the other way. Regardless of which way you do it, you cannot have any x's in your final result here. And everything up here in the original has to get transferred. You have to replace everything. There can't be anything left over either. So now I'm coming back to this. I'm going to integrate that. So that's u to the third over 3. I can write it that way. Plus c, because this is an indefinite integral. There are no limits. So 1/6, and then u is x squared plus 1, and then that's to the third plus c. Next. All right, so now we have a quotient. Anytime you have a quotient, the best place to start is making the denominator be u. So you want your u to be in the denominator, usually, almost always, pretty much. And again, you know, if you try a u and it doesn't work, try something else. So I'm going to make this entire denominator my u. And the other thing, too, when you're doing these, you can kind of look like, of course, with sine and cosine, the derivative of sine is cosine, and the derivative of cosine is negative sine. So when you have sine and cosine, you can actually possibly choose either one to be the u. But you're looking for a function in your integrand, and then its derivative in the integrand as well. And I want this to be my original function, because when I take the derivative of 2 is 0. Plus, it's always a good idea to make your u be in the denominator. So we'll take straight away, we'll look at our u and take the derivative. Like I was saying, that's going to be 0, and the derivative of sine is cosine. dt, get in the habit of putting that dt on there. Now we're going to come over here, and we're going to rewrite everything. So I've got this 6 up here. Let's bring it along. I like to bring it out front. Now right here I have cosine of t dt. Well, that's right here, cosine of t dt. That whole thing is du right here. It's gone. It's all taken care of. And then 2 plus sine of t is u. Look at that. That big old complicated thing got simplified down to this nice, easy integral. And then the integral of du over u, hopefully you got that one down. That's natural log. So we've got the 6, and then the natural log of u. Put that in absolute value bars, plus c. Come down the final line, replace your u with 2 plus sine of t plus c. I don't know why I'm out of breath today. It's weird. Okay, this next one is interesting. So if you try to make the denominator be your u, then right away you have to do du. And that's going to require the chain rule. I'm going to have 2 cosine of 2x times the derivative of cosine is negative sine of 2x times the derivative of 2x is 2. So I like to put my 2 out front. Squish a 2 in there. So I've got negative 4 cosine 2x sine 2x dx. Get that dx on there. I've got a problem, because if I do that, I've got this whole thing here would be my u, but then if I solve this for dx, I'm going to have du over negative 4 cosine 2x sine 2x equals dx. By the way, hopefully you're not writing all this down, because this is not going to work, but I'm just showing you what happens if you try it. Then you would end up with your integrand would have, well, I'll just do it real quick. You'd have du over all of this stuff down here, and it would all be with the x in terms of x. And then you would have the u over here too. You can't have a mix of x's and u's. So this is not going to work. Another u you might try is just the 2x. If you do that, you're going to have problems as well, because your u would be 2x, your du, and again, don't write this down because this isn't going to work. you would have that, and you'd end up with 1 over cosine squared of u. Actually, this could work. Maybe. I didn't think about it that way. Well, anyway, let me keep going here. So I lost track of what I was thinking because I got confused. Oh, anyway. So we got 1 over cosine squared of u, which is, 2x is u, and then the dx would be, dx is the same as du over 2. So I'd have du over 2, and I'd be integrating that. And actually, we can do this. Because what's 1 over cosine squared? Well, that is secant squared. That's the same as the integral of secant squared of u du. I'm going to erase this other stuff. This is just in a slightly different order than what I was going to do it originally, but this works just as well, and it's basically the same thing. So then you have to think back which function has a derivative that is secant squared, and that would be tangent. So the integral of secant squared u is tangent u. So the 1/2 is brought along. This is tan of u plus c, and then tan of u was 2x plus c. The way I was going to do it originally, or usually the way I do this one, is I usually rewrite it. I was going to write it as integral of secant squared of 2x dx at the beginning, and then make the u be 2x. So I just did it in a different order. And in this case, either order works. I don't really like that color. This is better. Integral of tan x dx. The way it's written isn't going to be too helpful. So, like on that last problem, we had to use a trig identity. We need to use a trig identity on this one as well. And the one that we want to use is that tan is sine over cosine. Now we have a quotient. The logical place to start with your u is in the denominator, so we want to make the denominator equal to u. Then we can take the derivative. And you could try this on your own first, and then come back and watch. The derivative of cosine is negative sine of x dx. Then we'll rewrite the integrand, so this becomes the integral. And I'm going to have my u down on the bottom. Cosine of x is u. And then the sine of x dx has to get replaced. Here's sine of x dx. So that would be sine of x dx is negative du. So I'm replacing this entire thing on top here with negative du. Oh, look, there's natural log again. Negative natural log of u plus c. And then to finish the problem, we simply replace the u. So it ends up being not too bad of a problem after all. Try this one on your own. So hopefully you chose the x squared plus 2x minus 3 to be your u. Immediately take the derivative. Then go back and replace everything. So we've got that entire thing as u squared. And then we've got x plus 1 dx right here. And I notice what happens if I pull out a 2 here? I have a nice result, don't I? There's my x plus 1 dx. So this entire thing is right here. So I could solve by dividing by 2. So I can replace this entire thing with du over 2. Integrate, bring the half along. That's going to be u to the 3rd over 3. Plus c, so that's 1/6. My u was x squared plus 2x minus 3 cubed plus c. Now, you could have done it the long way. You could have distributed this all out, squared it all out, and then multiplied this through and gotten a big long polynomial and then integrated that. But this way, the u substitution is way faster and much more fun too, by the way. Try this one on your own as well. Hopefully you chose the inner function to be sine of x, because it's being raised to the fourth, so this is an inner function. Immediately take the derivative, which is cosine of x dx. Come up to your integral, rewrite it, so that's going to be u to the fourth. And then the cosine x dx is right here, so it's equals du. We come up with this nice simple integral. Use the power rule, u to the fifth over 5 plus c. Replace the u. Actually, normally we would put the 5 there. Here, I'll write it better. Sine to the fifth of x over 5 plus c. Voila! Now this one has limits, so it's a definite integral. That means we're going to get a value. And what I'd like you to do is stop, pause, and do this one on your own. All right. Well, this one turns out to be kind of interesting because there's actually two different approaches you can take on it. So I'm going to have to do them both because I don't know which one you chose. So it looks to me like the inner function could be, well, you have to be careful on this. What's the derivative of tan? Well, the derivative of tan is secant squared. So I should make this my u, because here's my du right there. So u is tan x. My du is secant squared x dx. So it becomes very straightforward. Okay, so I've got u and I've got du. So the integral of that's u squared over 2. And there's no plus c this time. Now, this also brings us to another thing. There is a way you can do this. So right now with these limits, because these are in terms of x, these are your x, these are x's. What I can do after I integrate this, or actually right here even, when I get this written in terms of u, right here what we can do is we can write these limits in terms of u. So if x is 0, I can plug 0 in here, because here's my formula that tells me u. U is tangent of x. X is 0. So the tangent of 0 is 0. That means the u is 0. Now this one, I have x is pi over 4, so that u will be tan of pi over 4. And if you think about it on the unit circle, or whichever method you want to use, that's going to be 1. So what I've done is I've rewritten my limits in terms of u. So that means right here I am not going to replace my u. I'm going to leave it in terms of u because I've changed my limits in terms of u. And this is a kind of a shortcut. So I'm going to plug 1 in, evaluate it 1 squared over 2 minus, and then plug 0 in. So that ends up being 1/2. Now you can, so this is another option. This problem has all kinds of options. Option 2. You can leave your limits and replace the u with what it is. It's tan of x squared over 2. And keep the limits 0 to pi over 4. So everything's in terms of x. This is in terms of x, and your limits are in terms of x. And then you can evaluate it. So I'm going to have tan of pi over 4. I'm going to just write that squared. Oh, there's a 1/2. I think I'll just write that out front, brackets. Minus, and then tan squared of 0. Tan of pi over 4 is 1. 1 squared is 1. Minus tan of 0, 0, 0. And then there's the 1/2 hanging out outside, and you still get 1/2. Either approach is valid. You can see this upper one, leaving them in terms of u, is a little simpler looking. Okay, that was one way to do it. I do believe there is another way. Oh, You know what? I'm thinking of a different problem. Yeah, we're good. That's all I was going to do on that one. So that one's done. That wasn't so bad. Okay. So this is the almost last slide. This is a completely, well, I won't say completely, but this is a different objective, solving differential equations. We actually started this in 6.1. We did some solving. And so this one's a little different, though, because we have a y over here and x. When that happens, we have to do something called separation of variables, and it's very, very important. It's always the first step when your differential equation includes x's and y's. Number one, we must separate the variables. On the AP exam, almost every year it seems that they do one of these problems, and they're always worth 6 points, and always they give you a point right away for separating the variables. So you automatically get a point for this first step. And to separate the variables, I want to get the x's on the right-hand side and the y's on the left-hand side. And the way that we often can do it, the way these are often written, is you can divide. Sure enough, in this one we have 1 plus y squared. We're going to divide both sides by 1 plus y squared. That's how we're going to separate the variables. So let's write that down. Please show all your steps clearly. Write everything out. So I'm double checking and make sure I didn't make any mistakes. Second step is to integrate with respect to x. Write that over here. So step 2, integrate with respect to x. Do that in a different color. So I want to see the integral symbol and then dx here, and the integral symbol and dx. Then these dx's are going to cancel out. That's always going to happen. And so then over here on the left, you have an integral in terms of y. Over here on the right, you have an integral in terms of x. And now we can integrate. Well, okay, we have to do that yet. So we'll go ahead and do that. 1 over 1 plus y squared. Does that look familiar? We talked about that earlier today. That's inverse tan, or arctan. Arctan of y. You have to really pay attention to your variables here. Equals. Oh, what do we have here? Note, right away I see x squared, and right here I see its derivative 2x. So that gives me a clue that x squared needs to be my u. So I have to do a little bit of u substitution. U is x squared. Right away take du. 2x dx. Let's rewrite our integrand. So I'm going to have, oh, this is beautiful. Here's 2x dx. So this whole thing right here is du, and then this is e to the u. So I've got e to the u du. Beautiful. Nice and simple. Okay, I'm going to come down because I'm still in the process of integrating. The integral of e to the u du is e to the u. And I'm going to go ahead and just put the u back in there to save a space, otherwise I'd have to do another line. Now, this is an indefinite integral. We have to add c. If you forget the c, I think you lose a point on the AP exam. Just adding that c is worth a point, if I remember correctly. Remember the c. Okay, now we're going to solve for y, because we're trying to solve the differential equation. We're trying to figure out what y is. So to undo arctan, we take the tan of both sides. Make sure you're taking tan of the whole side, so you need those parentheses in there. That's critical. If you don't do that, you're going to get the wrong answer. Tan undoes arctan, y is left. So I've got the tangent of e to the x squared plus c. Now, oh, they didn't give us an initial condition. Often you'll have an initial condition here, but I'll just say it so you know you're going to use the initial condition usually to find c. And we don't have one, so they're just letting you start these off nice and easy. You have to have these parentheses. This is not the same as tan of e to the x squared plus c. That's not correct. Cool. These are, I just love these. I hope you guys like them too. There is an additional example that I have here that we're going to do in class, but if you're on your own right now, here's a couple of ones. These are additional problems, additional practice. What I'll do is I'll write down the problems, and then on the next screen I'll write the answers, and if you can't get it on your own, then maybe you could ask me during class. So solve, that's number 1. Solve that differential equation. Oh, by the way, that was the one we did in 6.1, isn't it, where we did the slope field. So you remember, you know what the solution is already because you remember the solutions from the slope field. So you'll know whether you get that right or not. And then another one is to solve dy dx equals x root y cosine squared of root y. That looks like a mouthful. All right, on the next slide I'm going to give the answers. So the answer to the first one is x squared plus y squared equals c. So it's a circle like we had expected. And then the second one is y equals arctan of x squared over 4 plus c, and then all of that is squared. And then we'll go back to the last slide. This one. Compare these two integrals. Which one can we use methods from today, meaning u substitution, and why can't we use u substitution on the other one? So which one can you use u substitution on? If you chose, that is a loud plane. If you chose this one, you are right. Because your u can be x squared plus 1, your du is 2x dx, and right here I have an x dx that I can replace with du over 2. So I could get the integral of u squared, and then x dx is the same as du over 2. That's kind of just the quick way of doing it. Up here, I mean, again, I would try, u equals x squared plus 1 and du 2x dx, and I'm going to have problems because I only have dx, so if I solve it, if I rewrite it, I'm going to have u squared, and my dx is the same as du over 2x. Well, I've got a mix of u's and x's. I can't work with that. So the u substitution is not going to work on that one. However, could you actually figure that integral out? And the answer is yes, because this is a binomial that's squared. You could square this out and get a polynomial and then integrate. So you actually can integrate both of these one way or the other. And that's it.